हेलो सर। सर आपका वॉइस नहीं आ रहा है क्लियर।
ओके अभी ठीक है।
अभी आया, हाँ अभी
हाँ
आया।
आई वाज ऑन म्यूट इट सीम्स। ओके
सर एक बात और थी सर। मैं अहमदाबाद आ रहा हूँ, मैं हाईवे में हूँ तो कभी नेट कभी चला जाता है आता है तो मैं ऑफलाइन हो जाऊंगा नेट नेट नहीं होने के कारण।
नो नो
तो
प्रॉब्लम,
सर मैं
नो प्रॉब्लम, द रिकॉर्डिंग विल बी देयर, यू कैन वॉच इट लेटर।
ओके सर।
ओके हाँ। So today we are going to look upon the conservation of momentum principle applied to fluid mechanics, and this is the most crucial essential part of our this course, conservation of momentum, because this will be the starting step towards deriving our full Navier-Stokes equation. So far what we have looked upon was the building blocks that we are going to build up to derive our conservation of momentum equations, conservation of angular momentum, and all sorts of other forms of equation. So laws of conservation of momentum will be expressed in differential form directly by applying Newton's law of motion to an infinitesimal fluid element. Here what we will do in your rigid body dynamics, generally you would come across that whatever external force is applied to a body of mass m, it will give it its acceleration, and this acceleration is nothing but the change in momentum with time. Okay, so rate of change of momentum basically is nothing but gives you the external force that was applied to that body. So this was our usual rigid body dynamics tells, or the Newton's law. Through Newton's law we know that from our basic understanding of basic courses. But here in fluid mechanics, not only F is equal to dp by dt or dmv, this is your velocity, dmv by dt. Not only this thing is sitting over there, but there is an additional term that is sitting over here. Because of this, the dynamics of fluid elements is such. Okay, so the external forces are not only the change in rate of change of momentum, but there are some additional terms that we call it momentum flux. We'll closely look upon this. Where does this come from? We'll actually derive this momentum flux that is crossing the boundary, or probably the momentum flux crossing boundary, so in minus out, in that sense. So this additional term will also come into picture if we talk about fluid elements. If we would not talk about fluid elements, then your usual Newton's law is, it would be this thing, F is equal to dmv by dt. Okay, so let's look closely how to derive this Newton's law, or the conservation of momentum for a fluid element. So for that, what I will do, I will assume a infinitesimal element which is subjected to all sorts of, which is subjected to tau ixj. Okay, in all the directions in this manner. So in all those manners it was subjected to the all sorts of stresses, okay, at that particular one point. So let's suppose this is my point which I am looking P. In order to do this, let me go back one step ahead. So this force I wrote that F external is equal to rate of change of momentum so we'll look upon here. Firstly, we will look upon these forces. Okay, so these forces can constitute body and surface forces. So body forces is straightforward to it is very straightforward to know. So we have rho g and I will if it is an infinitesimal volume dv volume, and then I can integrate it with dv, we will get the total body force on that body. But what about this surface force? These surface forces are a bit tedious to work with, so we'll look upon this surface forces closely right now. Okay, so these surface forces will be subjected because of the stresses that acts on a point. Okay, so this point, let's suppose this point is subjected to all sorts of stresses. What we'll take is, first we would want to emphasize on the surface forces, and then I will add these surface forces with body forces and club these together, and we'll see that these two surface forces will give me uh, the rate of change of momentum plus some additional term. And this is how we in this picture or in this flow will going to derive our conservation of momentum. Okay, let's first talk about this surface force. So we'll take up a fluid element. Let's suppose 3D element. I will take 3D element only. Okay, and this is my coordinate system. Let's suppose this is my x1 coordinate or x-axis. That side, right? I mean this side is my x2 coordinate or my y-axis. This is my small x. This is my y. This is my x3 or my y-axis. Okay, now let me write those forces, or first the stresses. Let me write down the stresses in x direction. So first, so for simplicity, I will write x1 direction stresses or forces that is acting on this fluid element. Okay, first only x direction. So what are all the things that are working in x direction are this. So on this face, so this is my x face, x direction face. So area normal is right hand side. Okay, so this is your tau 1 1. So basically, let me write it in this way. So this is your other stresses. So in z direction or in y direction, so this would be tau one face at one face in direction 2, in one face and direction 3. So essentially this state of stress would have been appropriate telling me this at this particular p point. But when I am traversing delta x by 2 dx by 2 distance right hand side, so at this point with Fourier, or sorry, with Taylor assumption, Taylor series expansion, this would be written as tau 1 1 plus of dou tau 1 1 by dou x1 times dx1 by 2, isn't it? Okay, similarly this would be having some other terms, but I will not consider that because I am considering only x direction forces. So I'll write all those stresses or forces that act along x-axis only. Okay, so on this particular face, left hand side, so let's suppose this is your left hand side face, and in left hand side face you will again have tau times, so this is not force, I'm not, this is just the stress. the stress should be multiplied by the area. So area is this total area, and this area would be dx2 times dx3. So now this is your whole force in x direction at one face only. Okay. Similarly, at left hand side, I can also write tau 11 minus of dou tau 11 dou x1 times dx1 by 2 multiplied by that area. That area is again dx2 times dx3, isn't it? So this is the normal force that is acting in x. What are the other forces that can act in x? So those forces on top, there will be one shear force that will be acting along right hand side, and rest of the forces will be on other direction, but I will not care. I'll care only this particular stress. So that stress will be what? Tau, that phase is 3, at 3 phase in one direction, and that would be, but this force, sorry, this stress will be written in terms of Taylor series expansion, because I am looking at this point. At this point, stresses will be simple tau 31, but at x3 distance, x3 by 2 distance, dx3 by 2 distance, it will be tau 31 plus dou tau 31 by dou x. You are traversing in x3 direction, dou x3 times dx3 by 2. This is your stress, net stress, and the force, if you talk about, you have to multiply with the total area that the stress is working. So this total area is x1 times x2, so dx1 times dx2, isn't it? So this is your x force on the top. Similarly, at the bottom surface also you will have state of stresses. Okay, and your state of stresses will be in this direction and other direction as well, but I will take only that direction. Okay, and that stress would be written as tau 31 plus, sorry, this would be minus, because I'm going down, minus dou tau 31 by dou x3 times dx3 by 2 total multiplied by dx1 dx2. Okay, now the last set of forces that I want to write is on front face, like the page face and the back of the page. Okay, this face. Okay, at this face, the state of stresses would be in x direction in this direction, and other direction stresses are this, and in this. So basically this x direction I have to take care only, because I am writing in x direction only. So I will sum up all the x direction. I will write that this is the force that is acting in x direction, which allows me to write the rate of change of momentum in x direction only, and then I can generalize it with all the directions. Okay, so this state of stress will be tau 2 phase in one direction, second phase on one direction, minus, so I am going back, I'm coming back, let's suppose I am coming back, dou tau 21 by dou x in x2 direction I am coming back, so and dx2 by 2. Okay, and multiplied with the whole area, that is dx1 times dx3. Similarly, the backside of thing can also be written. The stress will be acting on the right hand side, x1 direction, and that I can write with dot second phase one direction plus dot 2 1 by dou x2 times dx2 by 2 times the whole area dx1 times dx3. Okay, now let me summarize all the x directions in summation manner. Okay, let me write that and let's see what happens. So I'm summing all the forces in x direction or x1 direction, one direction. So I'm writing first force. So this and this blue color I will write. So tau 11 right hand side I'm writing. So this is my positive x direction. So this minus this minus this. So tau 11. So let me write it in color wise only, otherwise you will get confused. So the color wise tau 11 plus dot tau 11 by dot x1 dx1 by 2 times dx2 dx3 minus of tau 1, this one I'm writing, I'm sorry, minus of dot tau 11 by dot x1 times dx1 by 2 times dx1 dx2. Okay, this is my first force in x direction. What are the other forces? Other forces I can write with green first. So plus tau 3, or maybe I have to write, since I'll go one by one, so better to write black one first. So plus tau 21 plus dot tau 21 by dot x2. Shit, I'm really sorry, what happened? I had to keep that thing, I'm really sorry. Can I go back? I'm really sorry, I lost it. There are no other options, file to go back or something. I have to keep in mind that. Anyways, let me quickly write the equations, and this thing you remember, this thing you remember now. From next time I will be more careful. So that this direction was this one, x2 direction. Okay, let me write fx1 direction, that is, let me write it again for you guys. Tau 11, it was pretty clear, tau 11 by dou x1 dx1 by 2 times dx1 dx2 minus of tau 11 minus dot tau 11 by dou x1 dx2 by 2 dx1 dx2. Just and what other two terms will be there, and third term also will be there. Okay, let me go and do the algebra for the first term. So you'll see that this tau 11 and this tau 11 would be cancelled out. Okay, so similarly in other terms as well, every term it will be cancelled. So these two terms will be clubbed, since minus minus plus. So and this is dx1 by 2, so it will be 2 times dx1 by 2. So we are left with dot or x1 by x1 times dx1 dx2 dx3. Okay, first term. Second term will be dot or 1, it will be, sorry, 2 1. Okay, dot 2 1 by dot x2 times dx1 dx2 dx3 it will come, and this the elemental volume would be what? So this is dx1 dx2 and the height is dx3, so dv is equal to nothing but dx1 dx2 dx3. So these are coming out in dv's terms. So the last term is 3 1 by dou x3 dx1 dx2 and dx3. So this is what your surface force is. This, can I write this as dv, this as dv, this as dv? Okay, now I can write that my surface force per unit volume would be nothing but dot of 11 by dou x1 plus dot of 21 by dou x2 plus dot of 31 by dou x3. Do you guys agree upon this equation? Okay, do you agree? Yes, no?
Yes, sir.
Okay, so can I write in tensor notation here? Can somebody help me? Tell me how to write tensor notation here. So yes, this is nothing but the summation over tau of 1, 2, 3 are 1, 2 and 3. So this 1, 1 is there, 2, 2 is there, 3, 3 is there. So that is there is a summation sign. So I'll write tau j, and this is my one component, one component, one component, since I'm talking about force per unit volume in ith direction or one direction. So one direction is my, so this I can write 1 by, this is my dou x j, and summation sign I will omit. So this is how I am going to write my tensor notation. So this is what in one first direction. So in general, the force per unit volume, or not only the force, the surface force per unit volume in general direction, generic direction, generic I direction. ओके, अगर j के बारे में बात करेंगे तो j, k के बारे में बात करेंगे तो k. So this can be written as tau ji by, sorry, dou by x j, isn't it? Okay, so this is just, I have written surface forces right now. Okay, now let me go back and let me remind you that we have already deduced that in the last classes, that stress tensors were symmetric. Yes, stress tensors were symmetric, and we have shown this in our 2D element. Okay, by balancing the total torque over this, and we saw that the stress tensors will be symmetric. Okay, in 3 dimensions as well. So here we will apply that, and we will write the similar thing. This is nothing but this is my tau ij by dou xj. Both are same. Okay, we'll keep this in our hand as an equation 1, because I have calculated my surface force per unit volume in generic I direction will be like this. Okay, now the body force, let's take body force, because I told that I will be summing up this as body plus surface. So all the forces that are acting on the body gives him the rate of change of momentum. So the body force per unit volume in generic ith direction. Okay, so what was your body force? Do you guys remember how do we do that? So F is equal to mg, that is the body force, that is the gravity force. Because of the gravity force, because of its weight, mass, because of its weight, it is feeling this sort of body force. Okay, and body force per unit volume, if I do F by V, so this is per unit volume, F by V is equal to m by V g. So m by V is nothing but rho g, right? And if I am talking about in ith direction, so I will type I. So body force, so F surface ith direction, F body force in ith direction would be rho times gi. Okay, but it is there on earth that g only takes the role in kth direction only, but doesn't matter. If at all there are other body forces, you have to take care of in this manner. Okay, fine. So these two body forces I have written. Now I will tell that. Okay, so you remember our Lagrangian approach. These two forces gives the net acceleration to the body, and that was written, that we wrote in terms of what? So total forces per unit volume. In Lagrangian description, do you remember we have written rho times capital D ui by dt, and this d, capital D, was my total derivative. Isn't it? And this I can again write as rho dou ui by dou t plus rho, I will take common, ui, sorry, so in tensor notation, so basically what should we write there? So essentially, my, let's suppose my sum of my vector field, I have written this. So generally I used to write dou f by dou t plus u times dou f by dou x plus v times dou f by dou y plus w times dou f by dou z. Similar way I want to write it here. So this is nothing but, if I want to write in terms of tensor notation, dou f by dou t plus this, let's suppose this is my x direction velocity, x direction coordinate, I mean y direction velocity, y direction coordinate. So I can write uj dou f by dou xj, isn't it? Right? And this f here is ui, just replace f by ui here. Okay, so this is replaced by ui here, so this is replaced by ui, and I will write uj dou ui by dou xj, isn't it? This is simple. Now I can relate my total, these two total forces will be the sum up of these two, right? So I can write that this is nothing but my rho gi plus dou tau ij by dou xj, and this is it. This is the starting step towards our usual Navier-Stokes equation. Nonetheless, this equation is known as Cauchy's equation of motion. And this is the most generic equation of conservation of momentum. Okay, let me write it again here. Okay, let me write it again here in better manner. So I have written rho times, okay, dou ui by dou t. So basically I am writing things in ith direction, okay, plus u j dou ui by dou xj, right? This is my acceleration, okay, plus is equal to rho gi ith direction plus, in ith direction, what are the surface forces? What are the surface forces in ith direction? So ith direction, just replace 1 by I, so dou ji by dou xj, and this I can again write what? Dou ij by dou xj, right? So I can write here dou ij by dou xj. So this is the most beautiful equation that you would expect in fluid mechanics, and this is your starting step towards all fluid mechanics problems. This would be your just the starting equation, and this is the most generic equation. Also known as Cauchy's equation of motion. Why I'm telling most generic? Because you can actually substitute your surface forces in any manner. I didn't relate my stresses with deformation right now, or whether I don't know whether it is Newtonian or non-Newtonian, whether it is viscous or non-viscous. Uh, Obviously, viscous forces and pressure forces will come into picture, but this is the starting step or the most general step towards building Navier-Stokes equation, because this is the partial Navier-Stokes equation. I mean, comes from here only. Okay, and this was your body force per unit volume. This was your surface force per unit volume, and this is your acceleration in Lagrangian description. Okay, and this again can be written, this whole thing can be written by the capital D operator. Dou ui by capital DT is nothing but rho gi plus dou tau ij by dou xj. So this is also written over here, which is known as Cauchy's equation of motion. Now let me come to the usual linear momentum principle. So I told that I will relate this by F is equal to dmv by dt plus some additional term, right? Now let me relate these things here. Okay, how to come up with the proper fluid mechanics thing, proper conservation of momentum principle for fluid element, taking advantage of this Cauchy's equation of motion. So in order to do so, what I will want to do, I will start with the continuity equation. And continuity equation, I know that continuity equation is valid. Okay, and it should also, any fluid element should also obey continuity equation, and that continuity equation reads as, do you remember in the last class also, and in the previous classes we have actually done that. Del dot rho u is equal to 0. We have already seen that, right? Let me go back. Let me show you. In the last classes we have done that. So yeah, this was your continuity equation, and we have proved that also. So it is valid, and this should also obey. Now from this continuity equation, we'll try to write towards linear momentum principle as follows. What I will do, I will write my continuity equation in tensor notation. So this tensor notation would be written in terms of dou by dou x j rho u j is equal to 0. Now what I will do, I will multiply ui both side. Okay, so I can do ui is over here, and this it will be 0 again. So my equation will be ui dou rho by dou t plus ui dou by dou xj rho times uj must be equal to 0. This I know. Okay, now let me go back and take out this particular equation, this Cauchy's equation. Let me write it again. Let me keep it so that it should be saved. Go back. Let me save that once, because I don't want to lose it again. Okay, now that equation, that Cauchy's equation, I can write in this form. So dou ui in ith direction I am talking about, since I have multiplied ith here. So dou u by dot t plus what is that, uj dou, what is that, dou ui by dou xj, right? Isn't it? And is equal to rho gi, I'll take 5 more minutes, plus dot tau ij dou xj. Now since this thing is 0, I will add this thing in the left hand side here. I'll add this thing. So what I will do, I will add it here, and I will write it in this fashion. So I'll write ui dou rho by dot t. So this I have added additionally left hand side. So add left side. Okay, so what it will take, ui dou by dou xj rho uj, isn't it? Okay, this and this would be clubbed. So what I will do, I will club these two, and I will club these two. Let me see what happens. left hand side. So while clubbing that, can I write this equation as dou by dou t whole rho times ui? Isn't it? This is the derivative 2 times, and this can be written this way, the addition of these two. Similarly, the whole derivative of xj times rho ui uj, can I write that? Okay, one thing I've missed here. This is the bracket thing over here, no? So one row term will be here. I'm really sorry. So row term is multiplied over here also. Okay, the whole row. Okay. Now it can be clubbed. These two can be clubbed, and this can be written in this fashion, right? This must be equal to usual rho gi plus dou I j by dou xj. Okay. Now this is my differential form of momentum equation. Some differential form of equation. Okay. Now, just to make sure that things are coming at the whole volume, I'm going to integrate everything with the dv volume. I can do that. Okay. So let me write it again here. Dou by dou t rho ui dv plus dou by dou xj rho ui uj integration dv is equal to rho gi dv integration over the whole volumes. I want to, since I have taken elemental volume, I want to integrate with whole volume. I want to check with the whole volume what is happening with the whole fluid element, whole fluid region. This is dou tau ij by dou xj dv. Okay, now let's take one by one. This is my one, this is my second integral, third integral, and fourth integral. If we want to evaluate it one by one. So the first integral, can I write? How can I write this? So we'll use our usual. So this, since this is a fixed volume, so I can what I can do, I can remember we have learned a Leibniz theorem. According to Leibniz theorem, I can write this straight away. And what is this thing? Rho. So this is rho times velocity times volume. So rho and volume makes it mass times velocity. So mass times velocity is what? Linear momentum, isn't it? So I'll write this as capital M. Okay. So basically, so this is your differential momentum integrated over whole volume gives you the whole momentum, and this is the rate of change of momentum. This is nothing but dm by dt, nothing more than that, rate of change of momentum. So this is the rate of change of momentum that was usual for our solid mechanics. Okay, but because of these second terms, these terms, the other additional term will be coming out. Let's see that. Second integral I will take dou by dou xj rho ui uj dv. Okay, now apply Gauss's theorem, Gauss divergence theorem. So remember Gauss divergence theorem, what we used to do. So in Gauss divergence theorem, if we want to take any divergence of any vector field q, any vector field or scalar field, anything, dot q dv must be equal to q dA, isn't it? We can change our volume integral to the surface integral. So this is your volume integral, it will be changed to the surface integral in this manner. So I can write, so this is your jj is there. So there was a summation, and so basically this is what this is my del dot rho u, isn't it? Something like that. So I can actually write rho u I u j times dA j. Okay, and this term is integrated over whole area now. So cross divergence will be converted volume integral to the surface integral, area integral, and this is nothing but we call this a new term called m dot ith direction out, and this is nothing but the net rate of outflux of ith momentum. Ith momentum. Okay, and this is actually sitting over here, this is sitting over here, and this F is the total forces that usually take as F body and F surface. Okay, so third term we will take rho g dV is equal to what? This is nothing but force of body force in ith direction. Fourth integral I will take dot ij by dot xj dV. Again I can take Cauchy's divergence theorem again here, and I can write tau ij daj, okay, volume converted to surface integral, and this is nothing but tau times, I mean stress times area is nothing but the force, surface force in ith direction, and this would be clubbed to give you capital F is equal to rate of change of momentum, rate of change of linear momentum plus the net rate of outflux of ith momentum. So whenever you have a fluid element, fluid flow that is happening, you have to take care of, let's suppose you choose a boundary, you have to take care of your influxes and outfluxes, and you have to keep a track of that, and you have to write this term, and this will also contribute towards the force that will be acting on this particular element, isn't it? Not only the rate of change of momentum, but the net outflux of momentum also you'll have to take care additionally. And this will give me a range towards writing the full Navier-Stokes equation by including the viscous terms and the pressure terms, which we'll talk into the next class, and in the next class we'll talk about most about some constitutive equation, and then with some constraints we'll actually derive Navier-Stokes, the full and final Navier-Stokes equation, and that will end our first unit. Similarly, in the line of linear momentum conservation, we have angular momentum conservation as well in the similar line. So the net total torque is nothing but rate of change of angular momentum, rate of change of angular momentum, and angular momentum is defined by h. H is nothing but, so linear momentum was defined as, so your P was defined as mv, your angular momentum will be defined by r cross P, which is nothing but r cross mv, which is written over here in differential form. Okay, so that rate of change of angular momentum plus some additional term, that is the net rate of outflux of angular momentum through that control volume, and this could be summed up as an angular momentum principle, where these terms are written over here. So you can see the net total torque is nothing but the surface torque and the body force torque that might be acting. H is the usual H, and H out will be the flux that is cutting across the body by the angular momentum vectors. Okay. So we'll not go into the details, but yes, the linear momentum thing, I got into details, and we have come up with this particular conservation of momentum principle for fluid elements. And yes, and this will be a starting step and the last step towards a full Navier-Stokes equation derivation. Okay. Any question? Any question? No? Yes?